Imagine standing on a perfectly polished obsidian-black floor that stretches out forever in every direction. It is flawless, mirror-smooth, and completely reliable. You walk across it every day without a second thought. This floor is the foundation of your entire world. The laws of gravity that keep your feet planted, the speed of light that nothing can break, the way magnets pull on metal, the way atoms stick together to form everything you can touch. This is the standard model of particle physics, the most successful, precise theory humans have ever created. For 50 years, it has passed every test with almost impossible accuracy, predicting the behavior of particles to 10 decimal places, matching experiment after experiment like clockwork. It is the ultimate blueprint, the final word on how reality works. But what if, one morning, as you cross that floor, you hear it? A sound so faint it is almost easy to ignore. A tiny, barely there creak. You stop. You look down. The surface still looks perfect, black and gleaming. Yet the sound was real. It was the sound of a microscopic crack forming in the foundation of everything you thought you knew. That crack is not a thought experiment. It is happening right now, 17 miles beneath the border between Switzerland and France, inside the largest and most complex machine ever built, the Large Hadron Collider at CERN. For decades, physicists have been constructing a magnificent cathedral of knowledge, brick by theoretical brick. They believed they were nearing the end, that the final shape of the universe was almost complete. But the data is whispering something terrifying. The blueprint is wrong. The floor is cracking. And this one small glitch carries implications so deep they threaten to rewrite the very code of reality. We begin our journey not in the high-tech tunnels of CERN, but with something simple and familiar: the act of measurement. Think about the last time you measured something important. Maybe the distance of a road trip on a map, the time it takes to boil an egg, or the weight of flour for a recipe. In every case, you trusted that the rules stay the same. A mile is always a mile, a second is always a second, a pound is always a pound, no matter who is holding the ruler. This reliability is the foundation of everyday life. It lets us build bridges, launch rockets, and bake bread. We live in a world where cause leads to effect in predictable, measurable ways. The standard model is simply the most precise version of that same idea applied to the entire universe. It is a cosmic recipe that tells us exactly what the universe is made of, the fundamental particles, and exactly how they interact, the fundamental forces. It is a theory of breathtaking beauty and accuracy. It predicts the mass of particles, the odds of their decay, and the strength of their interactions with results that often match reality to 10 decimal places. For years, every experiment at particle accelerators confirmed it perfectly. It felt like we had finally found the source code of reality. The 4 pillars of this cathedral are the 4 fundamental forces. Gravity shapes the cosmos on the largest scales. Electromagnetism governs light, electricity, chemistry, and everything we see and touch. The strong nuclear force is the ultimate glue, binding quarks into protons and neutrons, holding atomic nuclei together against the massive repulsion between positively charged protons. The weak nuclear force is the quiet transformer, responsible for radioactive decay and the fusion in the sun that makes life on Earth possible. Inside this cathedral live the fundamental particles, the quarks that make up protons and neutrons, the leptons like the electron and the nearly massless neutrino, and the force carriers, the photons for electromagnetism, the gluons for the strong force, and the W and Z bosons for the weak force. And then there's the cornerstone, the Higgs boson, discovered in 2012, the particle that gives all others their mass by interacting with the invisible Higgs field that fills all of space. With the Higgs in place, the Standard Model was complete. The blueprint was finished. Many physicists believed we had reached the end of fundamental discovery, at least for the visible, everyday world. The cathedral was built, victory declared. But a finished blueprint is a dangerous thing. It suggests there's nothing left to find. And the universe, it turns out, is far too vast, too strange, and too stubborn to be fully captured by any single, final theory. The first real crack did not come from a dramatic explosion or a headline-grabbing new particle. It came from a subtle, nagging discrepancy so small it was almost invisible. The Moon's tiny, unexpected wobble. The Moon is the electron's heavier cousin, about 200 times more massive, but otherwise almost identical. Like the electron, it acts like a tiny bar magnet, with a property physicists call its magnetic moment, or G factor. In a perfectly empty vacuum, the Standard Model predicts this wobble with exquisite precision, down to 10 decimal places. But the vacuum is not empty. It is a roiling sea of virtual particles that flicker in and out of existence for the briefest instants, borrowing energy from the universe before vanishing again. These ghostly particles surround the muon like a fleeting fog, giving it tiny nudges that slightly change its wobble. The Standard Model calculates every known nudge, from photons to Higgs bosons, and predicts the exact result. For years, experiments matched the prediction perfectly. Then came the new, ultra-precise measurements at Fermilab and CERN. They measured the muon's wobble with such accuracy that the difference finally became clear. The real muon is wobbling just a tiny bit faster than the theory allows. The discrepancy is only about 0.0000000251, small enough to miss for decades, but now undeniable. To put that in perspective, imagine building the most accurate clock ever made, one that should lose or gain no more than 1 second over the entire 13.8 billion year age of the universe. That clock is the Standard Model's prediction. Now build a second clock using real data from the muon experiments. When you compare them, after billions of years, the second clock is off by less than 1/10 of a second. That tiny mismatch is the crack. It means the muon is being nudged by something the Standard Model does not account for. Something new, something dark, something hidden. It is the first experimental whisper that our perfect blueprint is incomplete, that there is physics beyond the visible 5% of the universe, and that the cathedral we built has a hidden basement we never knew existed. The crack is small, but it is real, and it is growing louder with every new measurement. The foundation is trembling, and the universe is about to show us how much we still don't know. The Standard Model is not a single discovery. It is the culmination of centuries of human effort to find order in the chaos of nature. It began long ago with Isaac Newton, who watched an apple fall and a moon orbit, and realized the same force governed both. He gave us gravity, a single rule that stretched from the ground beneath our feet to the farthest planets. It was the first great unification, showing that the everyday and the celestial obey the same law. Then came James Clerk Maxwell in the 19th century. He looked at electricity sparking, magnets pulling, and light shining, and saw they were not separate things, but different faces of one force: electromagnetism. He proved that light itself is an electromagnetic wave. Suddenly, the lightning bolt, the compass needle, and the rainbow were all expressions of the same underlying reality, carried by the photon. By the early 20th century, physicists peered deeper into the atom itself and found two more forces hiding inside. The strong nuclear force is the mightiest glue in nature. It binds quarks together into protons and neutrons and holds atomic nuclei together against the fierce electromagnetic repulsion between positively charged protons. Without it, every atom in your body would fly apart in an instant. The weak nuclear force is quieter but no less essential. It transforms one type of particle into another, driving radioactive decay and powering the fusion in the sun that gives Earth its warmth and light. These four forces, gravity, electromagnetism, strong and weak, form the four walls of the cathedral we call the Standard Model. Inside live the fundamental particles, quarks that build protons and neutrons, leptons like the electron and the ghostly neutrino, and the force carriers, photons for light, gluons for the strong force, W and Z, bosons for the weak force. Then, in 2012, came the final piece, the Higgs boson. It was discovered at CERN after decades of searching. The Higgs is not just another particle, it is the key that explains why anything has mass at all. Before the Higgs, all particles would zip around at the speed of light, massless and chaotic. But the Higgs field fills all of space like an invisible molasses. When particles move through it, they interact with the field and slow down, gaining mass. The Higgs boson is the ripple in that field itself, the proof that the molasses is real. With its discovery, the Standard Model was finally complete. The cathedral stood finished, every brick in place. For years, every experiment confirmed it. Particle collisions at accelerators matched predictions to astonishing precision. It felt like victory. The blueprint was done. Many believed we had reached the end, at least for the visible, everyday world of matter and forces. But a finished blueprint is a dangerous thing. It suggests there is nothing left to discover. And the universe, it turns out, has never been content to stay neatly drawn. The Standard Model is a masterpiece of the visible universe. The 5% we can see and touch, stars, planets, people, light, chemistry. Yet it is silent on the other 95%. It says nothing about gravity on quantum scales. It offers no explanation for dark matter, the invisible scaffolding that keeps galaxies from flying apart. It says nothing about dark energy, the mysterious push that is accelerating the expansion of the cosmos. And it cannot explain why the universe is made of matter at all. At the Big Bang, matter and antimatter should have been created in equal amounts. They are mirror images. Every particle has an antiparticle. When they meet, they annihilate in a flash of pure energy. If the amounts were perfectly equal, everything would have cancelled out, leaving only light. No stars, no planets, no us. Yet here we are, made entirely of matter. Something tipped the balance, one extra particle of matter for every billion pairs that destroyed each other. The Standard Model predicts perfect symmetry. We live in an symmetrical universe. That mismatch is one of its deepest failures. The cathedral is magnificent, but it floats in the air. It rests on no foundation for gravity. it ignores 95% of the cosmos. And it cannot explain why matter won the ancient war. The tiny wobble of the muon is the first real crack in the floor. It is the first experimental sign that something is pushing up from beneath, something the blueprint never drew. The cathedral is still standing, but the ground beneath it is trembling, and the universe is about to show us how much more there is to discover. The tiny, infinitesimal wobble of the moon, that difference of 0.0000000000251, is the most precise evidence we have that the Standard Model is not the final word. It is the ghost in the machine, a subtle, persistent error that points to a hidden influence. To appreciate the sheer difficulty of detecting this ghost, we must look at the scale of precision through the lens of time. Imagine you are a master watchmaker, tasked with building the most accurate clock in human history. This clock is so precise that it will lose or gain no more than 1 second over the entire 13.8 billion year age of the universe. This clock represents the Standard Model's prediction for the muon's behavior. Now, a rival watchmaker builds a second clock using a different method, the experimental result from the massive magnets at Fermilab and CERN. When you compare the two, you find that after billions of years, the experimental clock is off by a mere 1/10 of a second. For decades, this discrepancy was so small that physicists dismissed it as a statistical fluke. But as our tools grew sharper, the error didn't vanish, it grew louder. The experiment, known as muon G2, is a masterpiece of engineering. It involves a 50-foot diameter superconducting donut where muons are injected and forced to travel in a perfect circle. Because a muon acts like a tiny bar magnet, it precesses or wobbles as it travels through the magnetic field. If the vacuum were truly empty, the wobble would be simple to predict, but the vacuum is a roiling, chaotic sea of virtual particles that pop in and out of existence. These virtual particles, quarks, antiquarks, photons, and even Higgs bosons, surround the muon like a fleeting invisible fog, giving it tiny momentary nudges before they disappear. The Standard Model is so precise that it can calculate the cumulative effect of every single one of these virtual nudges, predicting the muon's G-factor to an astonishing 10 decimal places. Yet, the muon is wobbling more than the blueprint allows. This suggests the muon is being touched by something dark, a force or a particle that we have never seen before. Imagine a vast, dark ocean surrounding our small island of visible matter. This ocean is filled with dark matter and dark energy, governed by its own set of invisible forces. The muon, being 200 times heavier than the electron, may be heavy enough to briefly dip its toe into this dark ocean, interacting with a dark photon or a dark Z-boson before returning to our reality. This interaction is the ghost nudge. It is the first experimental thread that may lead us to a grand unified theory, weaving all the forces of nature into a single, elegant tapestry. But the muon is not the only messenger. In another corner of CERN, an experiment called LHCb was watching the decay of B mesons, particles made of a bottom quark and an antiquark. According to the rules of lepton universality, the universe should treat electrons and muons as identical twins, differing only in weight. If a B meson decays, it should produce electrons and muons in equal numbers. But the data showed a bias. The B mesons were choosing electrons more often than muons. To a physicist, This is like pouring flour and sugar through a funnel and realizing the sugar is flowing faster for no reason. The funnel of physics is favoring one ingredient. This is the second crack. It suggests the universe is not perfectly symmetrical. It is slightly, subtly lopsided. This lopsidedness is not just a technical error. It is the reason you exist. To understand why, we must travel back to the Big Bang. In that first fraction of a second, energy condensed into matter and antimatter. Antimatter is the mirror image of matter. An anti-electron is identical to an electron but carries a positive charge. When they meet, they annihilate in a flash of pure energy. If the Big Bang were perfectly symmetrical, the universe would have been a cosmic suicide pact. Every particle would have met its anti-twin, leaving behind a universe of pure energy. There would be no stars, no planets, and no people. Yet, here we are. The symmetry was broken. For every billion pairs of matter and antimatter that destroyed each other, one extra particle of matter was left over. Every atom in your body, from the iron in your blood to the calcium in your bones, is made from that 1 in a billion residue. The standard model predicts a symmetrical universe, but we live in an asymmetrical one. We need a bigger crack to explain this. The muon's wobble and the B-Messen's bias are potential clues to this origin story. They point to a new force that was active in the early universe, a force powerful enough to tip the scales and allow matter to win the war of annihilation. This is why the Large Hadron Collider is more than a machine. It is a monument to human curiosity. Buried 574 feet underground, this 17-mile-long ring functions as a time machine. Inside, 2 beams of protons are accelerated to 99.9999991% the speed of light. To do this, the ring must be colder than outer space, chilled to minus 271.3 degrees Celsius. When these protons collide, they recreate the conditions of the universe just a trillionth of a second after the Big Bang. It is in this violent, fleeting moment of creation that we find the muon and its mysterious wobble. The fact that it is wobbling more than it should means that, in that first critical second, an unknown force was at play. A force that has been hidden from us for 13 billion years. We are standing at the edge of the Standard Model's domain, looking out into the vast, dark territory of the unknown. The muon has given us a compass bearing. It tells us that the reality we perceive is only a fraction of the whole. The laws of physics we teach in schools are merely the local rules of our small neighborhood in a vast cosmic city. We must now prepare to enter the hidden sector, where extra dimensions and superpartner particles await to explain the glitches in our world. The journey into the fracture is just beginning, and what we find there may rewrite the very definition of nothingness. We must now step back and remember that science has always advanced through moments of fierce disagreement. When the entire community splits, when the old map no longer fits the new territory, and when the crack in the old picture becomes impossible to ignore. These were the turning points that reshaped our understanding of reality itself. One of the most famous was the clash between Albert Einstein and Niels Bohr over the nature of quantum mechanics. Einstein, the architect of relativity, could not accept the randomness at the heart of the quantum world. He famously said, "God does not play dice with the universe." He believed there had to be hidden variables, some deeper, deterministic layer we simply hadn't found yet. Bohr, on the other hand, embraced the uncertainty. He argued that the act of observation itself shapes reality, that the universe is not fixed and predictable, but probabilistic until measured. Their debate lasted decades, and it wasn't just about equations. It was about whether the cosmos is objective and knowable, or whether it is, at its core, uncertain and observer-dependent. Einstein never fully surrendered, but the experiments kept siding with Bohr. Quantum mechanics proved stranger than either man fully imagined. Another pivotal moment came in 1920 with the great debate between Harlow Shapley and Heber Curtis. At the time, most astronomers believed the Milky Way was the entire universe. The fuzzy, spiral nebulae were thought to be gas clouds inside our galaxy. Shapley argued the Milky Way was enormous and contained everything. Curtis insisted those spirals were separate, island universes, galaxies like our own, but unimaginably far away. The debate ended without a clear winner, but within a few years Edwin Hubble's measurements proved Curtis right. The universe grew from one galaxy to billions in a single stroke. The crack in the old map had become a chasm, and our place in the cosmos shrank overnight. The crack we are facing today, the muon's unexpected wobble, and the B-mesen's subtle bias, is our generation's version of those historic debates. It is the moment the Standard Model, our carefully built cathedral, shows its first real fracture. Like Einstein and Bohr, we are forced to ask whether the rules we trust are complete or merely local. Like Shapley and Curtis, we are being asked whether our visible universe is all there is, or whether there is a vast, hidden realm beyond our current maps. This crack is not just technical, it carries a deep ethical weight. Every major breakthrough in physics has handed humanity new power, and with power comes responsibility. The discovery of electromagnetism gave us light, communication, and industry. The unlocking of nuclear forces gave us energy, and tragically, weapons capable of ending civilization. The crack at CERN is no different. If it leads to a new force, a new particle, or access to extra dimensions, we are gaining tools that could reshape energy, propulsion, even the fabric of space-time itself. We could one day build engines that fold distance, harness vacuum energy, or manipulate gravity on small scales. These are not science fiction dreams. They are the logical next steps if the hidden sector is real. But power without wisdom is dangerous. We are still a young species. We have barely begun to understand the consequences of our own inventions. The crack is a reminder that we are not the masters of the universe, but its students. We must ask ourselves, when we open a door to the dark sector, what are we prepared to do with what we find? The muon's wobble is not just a measurement error, it is a moral question mark. It asks whether we are ready to wield forces we do not fully understand, whether we can balance curiosity with caution, and whether we can use knowledge to build rather than to break. The anthropic principle adds another layer of wonder and unease. Why are the laws of physics so perfectly tuned for life? If the strong nuclear force were just 2% stronger, stars would burn out in seconds. If gravity were slightly weaker, galaxies would never form. If the weak force were different, the sun could not fuse hydrogen into helium. The constants of nature seem dialed in with exquisite precision. The crack at CERN may offer a clue. If we live in a multiverse, then there are countless universes with different laws. We happen to exist in one where the numbers allow atoms, stars, planets, and conscious beings. The muon's wobble could be a sign that our universe is not unique, but one of many, each with its own local rules and hidden physics. As we prepare for the high luminosity LHC, we must brace ourselves for the end of old certainties. This upgrade will flood the detectors with 10 times more collisions than ever before, producing more data in 1 year than the machine has gathered in its lifetime. It is the ultimate test. If the wobble is real and caused by a new particle, the HLLHC will create it. We may see the first glimpse of a dark Z boson, a dark Higgs, or a superpartner. That moment would change everything, opening the door to the hidden sector, to the 95% of the universe we cannot yet explain. We are standing on the edge of the known, looking into the dark. Behind us is the finished cathedral of the Standard Model. Ahead is an ocean of possibility, extra dimensions, new forces, a deeper unity waiting to be found. The crack is not the end of science. It is the beginning of the greatest adventure in human history. The floor is trembling, but we are not afraid. We are explorers, and the universe has just invited us to step through the fracture and see what lies beyond. The search for what lies beyond the Standard Model has led physicists to some of the strangest ideas in science. Hidden dimensions. These are not places far away, like distant galaxies, but extra layers of reality curled up right here, at every point in space, too small for us to notice. To make this easier to picture, think about a garden hose stretched across your lawn. From a distance, it looks like a simple line, just one dimension, length. You could walk alongside it and see only that straight path. But get closer, or imagine being an ant crawling on it, and suddenly a second dimension appears. The hose's round circumference. You can circle around it, exploring a hidden loop that was always there but invisible from afar. That circumference is like a compact dimension, curled up small but real. String theory, one of the leading ideas to unite all forces including gravity, suggests our universe is like that. We see 3 dimensions of space, up-down, left-right, forward-back, plus time. But the math works only if there are 10 dimensions total. The extra 6 are curled up tiny, smaller than an atom, at every single point. We do not notice them because we are too big, like someone looking at the hose from across the yard. The muon's wobble might be our first peek into those hidden curls. Imagine the muon as a particle briefly dipping into one of those extra dimensions during its short life. There, it bumps into a dark force or particle we cannot see in our 3 dimensions, a dark photon or something similar. The nudge from that hidden world gives the muon its extra twist before it snaps back to our reality. That is why the wobble doesn't match the Standard Model. The model only accounts for our visible 3 dimensions. The crack is like an ant on the hose suddenly feeling the curve and wobbling off course. String theory hints at this because it tries to solve the big problems the Standard Model ignores, like gravity on tiny scales or why particles have the masses they do. In string theory, everything, particles, forces, is made of tiny vibrating strings. Different vibrations make different particles, like notes on a guitar string. To make the math work without contradictions, those strings need 10 dimensions to vibrate in. The extra ones are compactified, rolled up so tight they are invisible, but they affect how particles behave on small scales. One of the wildest ideas tied to this is the holographic principle. Imagine watching a 3D movie at the theatre. The story feels real. Characters walk, talk, and move in 3 dimensions. But it is all an illusion projected from a flat 2D film strip. The holographic principle says our universe might work the same way. The 3 dimensions we live in could be a projection from a lower dimensional surface at the edge of reality. Information about everything inside is encoded on that boundary, like a hologram. This idea came from black holes. Black holes have an event horizon, the point where nothing escapes. The amount of information a black hole can hold is tied to the area of that horizon, not its volume, like a 2D surface storing 3D data. String theorists like Juan Maldacena took this further, showing that in certain math models, a higher dimensional world with gravity can match a lower dimensional one without it. Our reality might be a hologram projected from a flat code at the universe's boundary. The amplituhedron takes this even further. Discovered in 2013, it is a geometric shape that simplifies how particles interact. In the standard model, calculating a collision between 2 particles can take thousands of equations, messy and full of steps. The amplituhedron boils it down to one simple volume calculation of a jewel-like shape in higher dimensions. No need for space or time in the math. They emerge as byproducts. Locality, things only affect what is nearby. And unitarity, probabilities always add to 100%, are not basic rules. They are illusions from the geometry. The muon's wobble could be a sign of this deeper shape peeking through. If particles are briefly touching that higher dimensional geometry, the extra nudge makes sense. It is like seeing a shadow on the wall wobble because something moved in the room behind you. The crack at CERN might be the first real evidence that our 3D world is a projection. That space and time are not fundamental, but emerge from something simpler, like a hologram from a flat plate. These ideas, hidden dimensions, holograms, geometric shapes like the amplituhedron, paint a picture of a universe far weirder than we thought. Reality is not a solid stage. It is a carefully woven illusion. The laws we see are like rules in a video game, useful for playing, but not the code running underneath. The moon's tiny glitch is like a pixel flickering on the screen, hinting at the program behind it. For everyday life, this changes nothing. Gravity still works, atoms still hold together, but for our understanding of existence, it changes everything. If dimensions are curled up everywhere, every point in space holds hidden worlds. If we are a hologram, then up and down, here and there, are just useful stories our brains tell. The amplituhedron suggests that particle collisions, the building blocks of everything, are just shadows of a perfect jewel in higher space. The crack is not a flaw, it is a doorway. It invites us to step beyond the familiar 3 dimensions and explore the hidden layers where the real rules live. We are like characters in a book suddenly realizing the page is flat, but the story comes from an author in a higher world. The muon is the first character to peek off the page. This is the ultimate scale shift, from a single wobbling particle to the architecture of existence itself. The universe is deeper, stranger, and more connected than we ever knew. The crack at CERN is our first step into that depth, a reminder that what we call reality is only the surface of something far more vast and beautiful. We must now step back and remember that science has always advanced through moments of fierce disagreement. When the entire community splits, when the old map no longer fits the new territory, and when the crack in the old picture becomes impossible to ignore. These were the turning points that reshaped our understanding of reality itself. One of the most famous was the clash between Albert Einstein and Niels Bohr over the nature of quantum mechanics. Einstein, the architect of relativity, could not accept the randomness at the heart of the quantum world. He famously said, "God does not play dice with the universe." He believed there had to be hidden variables, some deeper, deterministic layer we simply hadn't found yet. Bohr, on the other hand, embraced the uncertainty. He argued that the act of observation itself shapes reality, that the universe is not fixed and predictable, but probabilistic until measured. Their debate lasted decades, and it wasn't just about equations. It was about whether the cosmos is objective and knowable, or whether it is, at its core, uncertain and observer-dependent. Einstein never fully surrendered, but the experiments kept siding with Bohr. Quantum mechanics proved stranger than either man fully imagined. Another pivotal moment came in 1920 with the great debate between Harlow Shapley and Heber Curtis. At the time, most astronomers believed the Milky Way was the entire universe. The fuzzy spiral nebulae were thought to be gas clouds inside our galaxy. Shapley argued the Milky Way was enormous and contained everything. Curtis insisted those spirals were separate island universes, galaxies like our own, but unimaginably far away. The debate ended without a clear winner, but within a few years Edwin Hubble's measurements proved Curtis right. The universe grew from one galaxy to billions in a single stroke. The crack in the old map had become a chasm, and our place in the cosmos shrank overnight. The crack we are facing today, the muon's unexpected wobble and the B meson's subtle bias, is our generation's version of those historic debates. It is the moment the Standard Model, our carefully built cathedral, shows its first real fracture. Like Einstein and Bohr, we are forced to ask whether the rules we trust are complete or merely local. Like Shapley and Curtis, we are being asked whether our visible universe is all there is, or whether there is a vast hidden realm beyond our current maps. This crack is not just technical, it carries a deep ethical weight. Every major breakthrough in physics has handed humanity new power, and with power comes responsibility. The discovery of electromagnetism gave us light, communication, and industry. The unlocking of nuclear forces gave us energy and, tragically, weapons capable of ending civilization. The crack at CERN is no different. If it leads to a new force, a new particle, or access to extra dimensions, we are gaining tools that could reshape energy, propulsion, even the fabric of space-time itself. We could one day build engines that fold distance, harness vacuum energy, or manipulate gravity on small scales. These are not science fiction dreams. They are the logical next steps if the hidden sector is real. But power without wisdom is dangerous. We are still a young species. We have barely begun to understand the consequences of our own inventions. The crack is a reminder that we are not the masters of the universe, but its students. We must ask ourselves, when we open a door to the dark sector, what are we prepared to do with what we find? The muon has given us a compass bearing. It tells us that the reality we perceive is only a fraction of the whole. The laws of physics we teach in schools are merely the local rules of our small neighborhood in a vast cosmic city. We must now prepare to enter the hidden sector, where extra dimensions and super partner particles await to explain the glitches in our world. The journey into the fracture is just beginning, and what we find there may rewrite the very definition of nothingness. The anthropic principle adds another layer of wonder and unease. Why are the laws of physics so perfectly tuned for life? If the strong nuclear force were just 2% stronger, stars would burn out in seconds. If gravity were slightly weaker, galaxies would never form. If the weak force were different, the sun could not fuse hydrogen into helium. The constants of nature seem dialed in with exquisite precision. The crack at CERN may offer a clue. If we live in a multiverse, then there are countless universes with different laws. We happen to exist in one where the numbers allow atoms, stars, planets, and conscious beings. The muon's wobble could be a sign that our universe is not unique, but one of many, each with its own local rules and hidden physics. This idea of a multiverse turns the fine-tuning problem on its head. It is like asking why your house has a comfortable temperature. If there are billions of houses, each with random thermostats, you only find yourself in one that is livable. The others exist, but you are not there to complain about the heat or cold. The anthropic principle says we see a tuned universe because only a tuned universe can produce observers to see it. The crack might be the first evidence of the thermostat settings in our cosmic house, or even a glimpse of neighboring houses with different dials. The philosophical weight is immense. If the multiverse is real, then every possible outcome, every variation of laws that allows existence, plays out somewhere. In one universe, gravity is stronger, and stars collapse too quickly for life. In another, the weak force is different, and atoms never form. Ours is just one where the dice rolled right for carbon-based beings to emerge and wonder why. The crack at CERN could be our first peek through the wall into those other rooms, a signal from a neighboring universe or a force that leaks between them. This leads to questions that keep physicists up at night. Is the multiverse testable, or is it philosophy dressed as science? The muon's wobble and B-meson bias might provide the answer. If they point to extra dimensions or new particles that only make sense in a multiverse framework, then the crack becomes the key to proving the unprovable. It turns the anthropic principle from a convenient explanation into a testable prediction. In the end, the great debates of the past remind us that science thrives on tension. Einstein and Bohr argued over uncertainty because the quantum world refused to fit classical intuition. Shapley and Curtis clashed over scale because the universe was bigger than anyone imagined. Today's crack is our debate. Is the standard model the end, or just the beginning? The muon has taken a side. It says there is more, and in that more lies the potential for a unified theory that finally marries quantum mechanics and gravity, explaining not just the small room of particles, but the entire cosmic mansion. We are explorers at the edge of the map. The crack is our invitation to redraw it. The crack we have discovered at CERN is not just a scientific puzzle, it is a moral question. Every major leap in physics has handed humanity new power, and with power comes responsibility. The discovery of electromagnetism gave us electric light, telegraphy, and the internet. The unlocking of nuclear forces gave us clean energy, and, tragically, weapons that can end civilizations. The crack in the standard model is no different. If it leads to a new force, a new particle, or access to extra dimensions, we are gaining tools that could reshape energy production, propulsion, gravity itself, and even the structure of space-time. These are not distant fantasies. They are the logical next steps if the hidden sector proves real. But power without wisdom is dangerous. We are still a young species. We have only just begun to understand the consequences of our own inventions. The crack is a reminder that we are not the masters of the universe, but its students. We must ask ourselves, when we open a door to the dark sector, what are we prepared to do with what we find? The muon's wobble is not only a measurement error, it is a moral question mark. It asks whether we are ready to wield forces we do not fully understand, whether we can balance curiosity with caution, and whether we can use knowledge to build rather than to break. The anthropic principle adds another layer of wonder and unease. Why are the laws of physics so perfectly tuned for life? If the strong nuclear force were just 2% stronger, stars would burn out in seconds. If gravity was slightly weaker, galaxies would never form. If the weak force were different, the sun could not fuse hydrogen into helium. The constants of nature seem dialed in with exquisite precision. The crack at CERN may offer a clue. If we live in a multiverse, then there are countless universes with different laws. We happen to exist in one where the numbers allow atoms, stars, planets, and conscious beings. The muon's wobble could be a sign that our universe is not unique, but one of many, each with its own local rules and hidden physics. This idea of a multiverse turns the fine-tuning problem on its head. It is like asking why your house has a comfortable temperature. If there are billions of houses, each with random thermostats, you only find yourself in one that is livable. The others exist, but you are not there to complain about the heat or cold. The anthropic principle says we see a tuned universe because only a tuned universe can produce observers to see it. The crack might be the first evidence of the thermostat settings in our cosmic house, or even a glimpse of neighboring houses with different dials. The philosophical weight is immense. If the multiverse is real, then every possible outcome, every variation of laws that allows existence, plays out somewhere. In one universe, gravity is stronger, and stars collapse too quickly for life. In another, the weak force is different, and atoms never form. Ours is just one where the dice rolled right for carbon-based beings to emerge and wonder why. The crack at CERN could be our first peek through the wall into those other rooms, a signal from a neighboring universe, or a force that leaks between them. This leads to questions that keep physicists up at night. Is the multiverse testable, or is it philosophy dressed as science? The muon's wobble and B-Meson bias might provide the answer. If they point to extra dimensions or new particles that only make sense in a multiverse framework, then the crack becomes the key to proving the unprovable. It turns the anthropic principle from a convenient explanation into a testable prediction. In the end, the great debates of the past remind us that science thrives on tension. Einstein and Bohr argued over uncertainty because the quantum world refused to fit classical intuition. Shapley and Curtis clashed over scale because the universe was bigger than anyone imagined. Today's crack is our debate. Is the standard model the end, or just the beginning? The muon has taken a side. It says there is more, and in that more lies the potential for a unified theory that finally marries quantum mechanics and gravity, explaining not just the small room of particles, but the entire cosmic mansion. We are explorers at the edge of the map. The crack is our invitation to redraw it. The high luminosity LLHC is the next chapter in this story. This upgrade scheduled to begin full operation in the late 2000s, will increase the number of proton collisions by a factor of 10, producing more data in 1 year than the original LHC has collected in its entire lifetime. It is like replacing a flashlight with a massive spotlight. Suddenly, we will see details that were previously hidden in the shadows. The machine will be able to create and study particles that are too rare or too heavy for the current LHC to produce in large numbers. If the muon's wobble is caused by a new particle, perhaps a dark Z boson, a dark Higgs, or a superpartner, the high luminosity LHC will have the power to make it. Imagine the moment a new heavy particle is created, living for a fleeting instant before decaying into a signature captured by our detectors. Such a discovery would open the door to the hidden sector, to the 95% of the universe we cannot yet explain, and to the forces that tipped the matter-antimatter balance in the early universe. This is why the crack matters so much. It is not just a small error. It is a signal that the standard model is a local rule set, a map of our visible neighborhood, while a vast, dark territory waits beyond. The high luminosity LHC is our expedition into that territory. It is the tool that will tell us whether the crack is a dead end or a doorway. We are standing on the edge of the known, looking into the dark. Behind us is the finished cathedral of the standard model. Ahead is an ocean of possibility, extra dimensions, new forces, a deeper unity waiting to be found. The crack is not the end of science. It is the beginning of the greatest adventure in human history. The floor is trembling, but we are not afraid. We are explorers, and the universe has just invited us to step through the fracture and see what lies beyond. The moon has spoken. The crack is open, and the journey is only just beginning. The study of the subatomic world is, ultimately, the study of connection. It shows us that at the most fundamental level, there is no such thing as an isolated object. Everything is part of a single, roiling sea of energy and information. If we can learn to see the world through the lens of the crack, to see the hidden connections and underlying symmetries, perhaps we can learn to live in greater harmony. The muon's wobble is a call to realize that we are all made of the same broken symmetries and the same stardust. We are all part of the same cosmic glitch. As we move toward the future, the LHC is being upgraded to the high luminosity LHC. This upgrade is like replacing a spotlight with a massive floodlight, increasing the number of collisions by a factor of 10. It will produce more data in 1 year than the machine has produced in its entire lifetime. This is necessary because the crack is so subtle that we need an overwhelming amount of data to reach 7 sigma certainty, an undeniable fact. The HLLHC will be the ultimate test. If the wobble is real and caused by a new particle, the HLLHC will have the power to create that particle. Imagine the moment a new, heavy Z prime boson or a dark Higgs is created, living for a fleeting instant before decaying into a signature captured by our detectors. Such a discovery would fundamentally change our understanding, leading to a new model that includes the hidden sector and the solution to the matter-antimatter mystery. The ultimate goal remains the theory of everything, a single equation describing all forces, including gravity. The crack is the first step toward this unification. Imagine the universe as a vast symphony where the standard model provides the score for the strings and brass, while the percussion, gravity, and the fifth force plays an unwritten part. The crack is the moment the strings finally hear the percussion, forcing us to search for the unified score that brings all instruments into harmony. It reminds us that every subatomic event is connected to the fate of the entire cosmos. We began this journey certain of our reality, but we end it filled with wonder at the edge of a dark ocean. The map is blank, but we are not afraid. The crack is not a collapse, but a sign of growth, the universe expanding its own definition of reality. This journey from a polished floor to a cracked, multidimensional reality is a journey into the heart of scientific uncertainty. The most profound consequence is the unraveling of certainty itself. We build our lives on predictable rules, trusting that the sun will rise and that gravity will hold us to the earth. This certainty is our psychological foundation. Imagine you're a master chess player who knows every rule perfectly. But then, in the middle of a match, your opponent moves a pawn 2 squares diagonally. You protest, but your opponent simply explains that the rule you knew was only a local approximation, and you have just witnessed the first exception. The muon's wobble is the pawn moving diagonally. It tells us the standard model is not the final, immutable law, but a local rule set that breaks down at the boundary. This forces us to consider that the laws of physics are not eternal ideals, but emergent properties of a deeper reality. What if the fundamental constants of nature, the speed of light or the charge of an electron, are merely the current settings of a cosmic dial? The crack suggests a vast, interconnected multiverse of possibilities. In this view, our universe might be just one brain or membrane floating in a higher dimensional space. While the forces we know are confined to our brain, gravity and the fifth force can leak into the extra dimensions. Imagine a sheet of paper floating in a swimming pool. The creatures on the paper only know their two-dimensional world, but a wave in the pool can pass through the water and affect the paper from a dimension they cannot perceive. The muon's wobble is that ripple from the pool. This is the ultimate scale shift, from a subatomic particle to the very structure of the cosmos. The tiny crack is a window into the possibility of infinite universes, each with its own local rules and unique history. The beauty of this uncertainty is that it re-establishes science as a perpetual journey. The moment we thought we had the final answer, the universe politely corrected us. The crack is an invitation, telling us that the real adventure is just beginning. To further deepen this narrative, we must look at the life of the particle itself. The muon is born in the heart of the LHC's collision chambers, a fleeting product of two protons smashing together. Its life is a cosmic tragedy that lasts for only 2.2 microseconds, a single sharp intake of breath in human terms. In that blink of an eye, it is born, it travels, it interacts, and it decays. Yet, because it moves so close to the speed of light, it experiences time dilation, allowing it to complete several hundred laps around the 17-mile LHC ring from our perspective. It is a traveler that defies its own lifespan. During this brief journey, the muon acts as a subatomic spy. Its mission is to report back on the forces it encounters. While it meets the familiar agents of the standard model, it also reports an extra nudge from a dark agent in the hidden sector. This interaction is a quantum fluctuation, a momentary borrowing of energy. For a split second, a dark photon or a neutralino appears in the cloud of virtual particles surrounding the muon. giving it a tiny, unpredicted twist before vanishing. The muon then decays, but its final message, the data of its anomalous wobble, is the most important piece of evidence in modern physics. This reminds us that the universe's most profound secrets are often hidden in the most fleeting and unstable phenomena. The crack is a dynamic event, a glimpse into the chaos of creation. This discovery is the culmination of decades of human effort and sacrifice. The LHC project is a collaboration of over 10,000 scientists from more than 100 countries. A modern Tower of Babel reaching for the infinitesimally small. Aligning its 9,300 superconducting magnets requires a level of remote precision comparable to shaving a man's face on the moon, using a razor operated from Earth. The cost is measured in human time, decades of careers and thousands of sleepless nights. The muon's wobble is the payoff for this sacrifice, a moment when the universe finally rewards our persistence. But it also requires the humility to kill your darlings. For a generation of physicists, the Standard Model was their life's work, and the crack is a challenge to that intellectual legacy. It is a lesson that the universe is always more creative and mysterious than our best theories. Our role is not to find the final answer, but to find the next question. And the crack at CERN is the most exciting question mark of our time. As the lights of the LHC dim for the night, and the 17-mile ring continues its silent, cold vigil beneath the Earth, the protons continue their frantic race, and the crack continues to whisper its secrets. The floor is cracking, the blueprint is failing, and the reality we knew is unraveling. But in its place, a new reality is emerging, a reality of infinite dimensions and profound symmetries. A reality where the glitch is the source of all creation and the crack is the doorway to the infinite. Rest now in the knowledge that the universe is in good hands, the hands of those brave enough to look into the fracture and see the light. The final silence is here. The journey is complete for tonight, but the mystery is eternal. Good night, traveler of the cosmos. May your dreams be filled with the music of the spheres and the light of the hidden dimensions. As we reach the end of this journey, let us pause and look back at the path we have walked together. We began with the image of a flawless obsidian floor, the Standard Model, the most precise and successful theory ever built, a blueprint that seemed to explain everything we could see and touch. We heard the faint creak, the tiny crack in that foundation, and followed it down into the depths of the muon's unexpected wobble and the subtle bias in B-meson decays. Those small discrepancies grew into something much larger, a whisper that the cathedral we constructed is incomplete, that the visible 5% of the universe is only the surface of a far deeper, darker reality. We explored the hidden sector, supersymmetry with its promise of super partners, extra dimensions curled up at every point in space, the holographic principle suggesting our three-dimensional world might be a projection from a flat boundary, and the amplituhedron reducing particle collisions to elegant geometric shapes in higher dimensions. Each idea stretched our imagination further, reminding us that reality is not the solid stage we assumed, but a layered, interconnected tapestry where the laws we know are only local rules. We revisited the great debates of the past, Einstein and Bohr wrestling over certainty and uncertainty, Shapley and Curtis expanding the universe from one galaxy to billions, and saw that today's crack is our generation's turning point. It forces us to ask whether the standard model is the final truth or merely a map of our neighborhood, while a vast, hidden landscape waits beyond. The anthropic principle added its own quiet challenge. Why are the constants of nature tuned so perfectly for life? If a multiverse exists, then we simply occupy one of the rare universes where the dials are set just right for atoms, stars, planets, and minds to emerge and wonder why. The high luminosity LHC stands ready as our next great tool, a floodlight that will illuminate the shadows where new particles may hide. It will produce collisions at rates that dwarf everything before it, giving us the statistical power to confirm or refute the anomalies with certainty. If a dark Z boson, a dark Higgs, or a superpartner appears in the data, the crack will become a doorway. We will step through into a reality that includes the missing 95%. That explains the matter-antimatter imbalance, that perhaps unifies gravity with the quantum world. Yet the deepest lesson is not in the particles or the forces. It is in the humility the crack demands. For a generation of physicists, the standard model was a life's work, a completed masterpiece. The wobble is a gentle but firm reminder that the universe is always more creative, more mysterious, and more generous than our best theories. It does not hand us final answers, it hands us better questions. Science is not about reaching the end of the map. It is about discovering that the map was always too small. We began this exploration certain of our reality, standing on what we thought was solid ground. We end it filled with wonder at the edge of a dark ocean. The floor is cracking, the blueprint is failing, and the reality we knew is unraveling. But in its place, a new reality is emerging. A reality of infinite dimensions, profound symmetries, and hidden connections. A reality where the glitch is not failure, but the source of all creation, and the crack is the doorway to the infinite. Look up tonight. The stars still shine. The laws still hold. But now you know they are only the surface of something far greater. The moon's wobble is a whisper from that greater depth, a reminder that we are part of a universe that is still being born, still revealing itself, one infinitesimal surprise at a time. This is Cosmo Depth. Thank you for joining me on this descent into the fracture. If the crack has stirred something in you, if it has made the night sky feel both more familiar and more mysterious, then share this journey. Hit like, subscribe, and turn on notifications so you never miss the next whisper from the cosmos. Until we meet again, keep listening. The silence still has secrets to tell, and we are the only ones left who can hear them.